Okay, now that we've done the energy in the fresh milk and the energy from that's given off in terms of steam at 65 degrees Celsius, the trick is now calculate the energy, the enthalpy in the evaporated milk. The equation is the same, 5,000 kilogram of evaporated milk, the heating capacity, and then 65 degrees Celsius in relationship to 0 degrees Celsius. The challenge is now we do have to calculate the new percentage of fat and the new percentage of non-fat solid because water is now removed. Basic algebra, I can say, and needs a little bit of clear thinking. So I've formulated these tables here. So this is what happened. This is how much we had in the beginning from the fresh milk. And so let's just turn it into a real number. Just assume it's 100 liter. In the end, everything will be percentage, so it would be fine. Sorry, it's a little blurry. Like, there's no way I can make it a little more sharp here. Okay, so this is 100 liter. So this is how much of fat, non-fat solid, and water. So what happened now is during the evaporation, 60 kilograms, 60% of the moisture is now evaporated. But these two amount, the fat and the non-fat solid doesn't change. There's still the same amount of fat and non-fat solid in our end product. The only thing that changed is the net amount of water. The total will be 40 degrees Celsius. No, sorry, 40 kilogram because there was 60 kilogram of water is gone. So what I need to do is now converting 3.25 kilogram of fat into a percentage. So I have 3.25, sorry, it's not very clear. 3.25 divided by 40, 8.5 divided by 40, and then 28.25 divided by 40 to get, it's a little messy, 70.625%. Plugging these percentage as a decimal back into this equation that we've used a couple times already, then we can get the heating capacity of the evaporated milk. Then plugging it back to this equation here, we know the energy in our evaporated milk is this. Now we have so according to this equation, we know the three components. We will then be able to find the amount of heat that we need from our steam per hour, because we're talking about an hour of production. So this is how much steam we need. Let me just, because so here, sorry, I had to skip it. So this is the amount of energy we need from our steam, condensing steam. The steam is giving us all of its energy from vapor to liquid. So we will use our steam energy table. Remember, we are using it at 120 degrees Celsius. So look for those number. So I had the table somewhere. It's not handy. But look at the table. You will find the table. You will find this number. And then you can solve. This is how much of steam we need in terms of mass in kilogram. On the very same table, you can also find the density of the steam at 120 degrees Celsius. So this is this. I believe if I actually keep track of my significant figure, I believe the final answer should have only 2 significant figures. But I haven't done the actual number. But here, 2 significant figure or a number like this, I'm not going to take marks off on your final exam. There are so many, or on your assignment. So this is the mass of steam we need and the mass of steam we need, the volume of the steam at 120 degrees Celsius.